Greetings everyone. Welcome back to Calculus 1. It's time to continue our discussion into the world of antiderivatives. It's going to seem like we're going to go off the beaten path for a while, especially in this section. Because what we're going to be doing is we're going to be approximating areas drawn with graphs that have to do with functions. Okay? But I promise you these are going to deviate and swing back around to being related to antiderivatives. We just have to build up a few topics before we get there. Okay? First, before we even get to the approximating areas portion, we need to talk about sigma notation. And basically, this is just a mathematical way to shorten up a sum of a list of numbers. Okay? So whenever you see the capital sigma, that's this E looking thing, that's a capital Greek sigma. That's used to talk about the sum. It's actually their version of S, right? The capital sigma was. So what this is what you'll see is the sigma will be the symbol for, hey, by the way, we're about to add a big list of things, okay? And then once you see that, you look beneath and it'll tell you what the counter variable is. This variable is going to be my counter, and he's going to count from A to B one at a time, okay? So if I say that I have some function of I, right? I need to have some function of whatever the counter variable is because I have to have somewhere to plug these values in. Then I just start by counting the A value first, right? So that would be f of A. Then I count up. It would be A plus 1, then A plus 2. And each time I get a new value, I'm plugging it into whatever this expression was, this function expression. And then each one of those answer values, I'm going to add in one big long summation. Okay? So that's what they call this. This is a summation. Let's get some examples. So here I have the summation where I is going to count from 8 to 11. Alrighty then. So what I'm going to be doing is, this is going to be equal to, when I is 8, 8 squared is 64, minus 1 is 63. Plus, when I is 9, 9 squared is 81, minus 1 is 80. Next, plus, when I is 10, right? So 10 squared is 100, minus 1 is 99. Plus, next, when I is 11, right? That's going to be 121 minus 1, which is 120. Okay? Then the answer to the summation is going to be what I get when I actually sum all of these up. So I've got 143, 242, and 362. Right? Okay. So this summation equals the value 362. Next, I have the summation where n is counting from 0 to 4. Okay? So then this is going to be equal to 3 times 0 plus 7 is 7, plus n then goes to 1, right? So then that would be 3 times 1 plus 7, 10. When n is then 2, right? Here I have, let's see, let me go ahead and count it out for you. N is 0, n is 1, n is 2, right? So that would be 6 plus 7 is 13. Then n is 3, and n is 4. So when n is 3, I get 16, and when n is 4, I get 19, right? Okay. So I've got 17 plus 13 is 30. Then 46, 45, and 20 is 65. Okie dokie. Now look here. This is a summation, and notice there's no i's over here. That's okay. It just means that I'm adding up a 5 over and over again, right? So when I is 1, I'll get 5. When I is 2, I'll get 5. When I is 3, 4, 5, 6, 7, and 8, right? I counted from 1, 2, 3, 4, 5, 6, 7, and 8, right? All the way up to here. Here I equals 8. It just happened to be 5 every time because there was no variable, right? So I have 8 5s, right? 8 times 5 is 40. Okay. There's a property here that we're going to talk about whenever you sum a constant. Okay. We're going to write down a list of properties in a minute, and this is one of them. When you sum a constant, it ends up just being multiplication, because that's how we define multiplication, right? Okay, now here are some other things that can come up when you use summations. And by the way, we're not just going to be using summations for these next few sections now. This type of terminology is going to come up again later on this semester a little bit, and in Calculus 2 when we start doing infinite series. Okay, so don't just shrug this and throw away the knowledge here. You need to know how these summations work. So then, on this one, I'm going to start with r equals 1, right? So that gives me negative 1 to the 1 over 1 plus negative 1 squared over 2 plus negative 1 to the 3 over 3, negative 1 to the 4 over 4 plus negative 1 to the 5 over 5, right? Because I'm counting r equals 1 to 5. So let's see, what will that give me? I've got negative 1, right? Plus negative 1 squared is just 1, so I have 1/2. Then negative 1 to the 3rd is negative, so that's negative 1/3. Next, I'll have plus 1/4. And then finally minus 1/5. And of course, to sum all of these up, I'll need a common denominator for 2, 3, 4, and 5. So let's see, 6, well, 4 and 5 both go into 20, and that covers the 2. And then with the 3, it's going to have to be 60, right? I'm going to have to add these up into 60ths. So that's going to be negative 60 plus 30, right? Minus 20 plus 15, and then minus 12, all over 60, right? So let's see, negative 30, negative 50, and then plus 3. So negative 50 plus 3 is negative 47 over 60, right? Next, I'm talking about the summation here from where n is going to count from 0 to 4, right? The bottom number is where we start. Don't forget, 0 to 4 here. And then my function here has a new symbol possibly, if you haven't seen the exclamation point. That's called a factorial. The factorial of a number means to multiply from 1 all the way up to that number. Okay? So n factorial is 1 times 2 times 3 times 4 all the way up to n, and you just multiply that string of numbers. Okay, that's what it means to do a factorial. So in this case, what I've got is when n is 0, I've got negative 2 over 0 factorial plus negative 2 over 1 factorial plus negative 2 over 2 factorial, negative 2 over 3 factorial, and negative 2 over 4 factorial. So then another little side note, 0 factorial is defined as 1. I know that doesn't fit the other definition that I gave you, but it goes along with our number theory that we have for our number system. 0 factorial needs to be defined as 1, not necessarily calculated, just it's defined as 1. Okay, so what I have is negative 2 over 1, and then negative 2 over 1 again, because 1 factorial, by the definition here, would just be 1. So I have minus 2 again. Next, I'm going to have negative 2 over 2 times 1 is 2, right? Because 2 factorial is going to be 1 times 2. Next, I'm going to have minus 2 over 3 factorial, which is going to be 1 times 2 times 3, which is 6. Okay. Next, I'm going to have minus 2 over 4 factorial, which is going to be 1 times 2 times 3 times 4, which is 24. Right? The good thing about factorials is if you have them in order like this, the common denominator is going to be the one on the end, right? Because they all were multiplying up to get to it there. So let's see, what do we have over 24 here? Let's see, we have negative 4 times the 24, right? So that's 80 and 16, so that's negative 96. And then right here, I'm going to have times 12, so minus 24. And then times 4, so another minus 8. And then this is already in 24, so minus 2 is going to equal to what over 24? Let's see. I've got 120, 130, negative 130 over 24, which would be negative 65 over 12. Right? All right. So don't let any of the symbols throw you off. Just remember the summation means to add up, right? The sigma means to add a string of numbers, a list of numbers. And the function, the expression in here is just what you're going to plug in the counter at every step to create the list. Here are a couple of properties that we need to notice here that we're also going to do. This was one of the properties, right? If you have a constant, it turns into multiplication. Here's another thing. If you have two of the same expression in different countings, right, then you can use the numbering system to help you shorten your ride here. Let me show you what I mean. If I write out the full summation here, I'm not going to use any of the properties yet. I'm going to write out this full summation and this full summation, and then I'm going to rewrite what the answer would have looked like as a summation, right? So if I'm counting from 1 to 10 and I'm using some function of n here, then that's going to be f of 1 plus f of 2 plus f of 3 plus 4, 5, 6, 7, 8, 9, I almost fit it, huh? Plus f of 10. Okay, that's just this piece. Then next, the summation from 1 to 6 of the same expression. right? F of n, same expression, but this one's only counting 1 to 6, and it's subtracting them. So I would then, from this, have minus f of 1, minus f of 2, minus f of 3, minus f of 4, minus f of 5, minus f of 6. Technically, what I would have is minus and then the addition of all of these. But notice, since this is a summation, I can just make the negative parse into each one. But look at what's happening here. The f of 1s are going to add to 0, f of 2s, f of 3s, f of 4s, 5s, and 6s. Those are all going to add to 0. And notice the only thing I have left is f of 7, f of 8, f of 9, and f of 10. So these two put together are equal to the summation where n is 7 to 10, right, of the expression f of n. So let's use a little bit of addition sense here. This is a string of additions. This is a string of additions of the same thing. If I'm having the objects from 1 to 10 and I'm taking away the objects from 1 to 6, then I'm only going to be left with the summation of the objects from 7 to 10 of that same expression object. Okay? So that's one of my properties of the summations, that you can actually combine these things. All right. Next, right here, this one. Let me separate out here. This is just 3f of 5, right? Because I'm starting at 5, plus 3f of 6, plus 3f of 7. Right, from 5 to 7. But do you notice how they're all multiplied by the 3? Because that's what the expression told me to do. I could have done this. I could have factored the 3 out since they all have it, right? I could have just done this. And then f of 5 plus f of 6 plus f of 7. Like that. But then what's this right here? That's just the summation of that expression f from 5 to 7. So I have 3 times the summation I equals 5 to 7 f of I. So here the property is, if I have a multiplied number times an expression on the outside, then I can actually wait to do that multiplication. I can put it on the outside, and I can wait to do it after I've actually done the summation. Okay, so on something like, say, this one right here, notice how they all have the -2, right? I could have pulled that -2 out at first and then just focused on the inner summation and then multiplied the -2 to the sum afterwards. That would have worked because it's the same number multiplied by all of them. Okay? But not like that on any of these other ones. See, there's not a multiplied number on these lists. I would have to find other ways of splitting these things up. Okay? This is just to give you a beginning taste. Now let's go take a look at the actual properties of these, and I'll show you how we can work these without having to list out all of the terms like we've been doing. So let's talk about the ways that we can do these summations in a more efficient, quicker way. So let's get some properties of the sigma notation. First of all, as we saw in one of the previous examples already, if you have the same expression and you have different limits, but the limits line up, like for example, I have from A to B, and then I have from B to C, and I'm adding those, then that's the same thing as just adding everything from A to C. Vice versa, if I'm adding everything from A to B, and then I'm subtracting everything from A to C, then I'm only going to be originally adding everything between C and B, given that C is some number in between A and B, of course, right? Another way that these summations can be split up is if you have a summation with an addition in there of two different expressions, then it's just as good to add the expressions separately up in their own summations and then add the sums afterwards, because it's all addition. This summation is adding a long list of things up, and if you have things in there that are adding things also, well, then I can just add in a different order. It's just the commutative and the associative properties of addition, right? 2 plus 3 and 3 plus 2, right? It doesn't matter which way you add it. 3 plus 2 plus 5. You could also do 3 plus 5 plus 2, or you can do 5 plus 3 plus 2, things like that. That's why this rule right here works, because all I'm doing is rearranging some additions with other additions and subtractions. Okay? We saw a straight up example of this one, and I wrote it out right here. If I'm summing up something that doesn't depend on the counter variable, then this is just some constant. Doesn't matter which way you write it. If there's no, the counter variable here is I, since there are no i's in here, then this is considered a constant, even if it's a letter, if it's a crazy symbol, whatever. Okay, if it doesn't depend on the counter, it's constant. So in this case, what I would do is I would take the high number minus the low number, b minus a, plus 1. Think about that for a second. I'm counting, but I also starts off as that first number. If I do b minus a, that's the number of counts between b and a. But then I also have to count a itself, hence the plus 1. And that's how many of these counts I have, b minus a plus 1, times the constant. I'm just going to have that same constant over and over again. And here's that example that we had in the last scene. Summing from I equals 1 to 8 of 5, I just do 8 minus 1 plus 1, which will give me 8 times 5, gives me 40, which is what we got. Okay, now these next three are crucial to a lot of our area approximating later that we're about to do. And that is how to sum lists of powers of whole numbers. Okay, so for example, if I want to sum all of the numbers from 1 to n, right? See, I is just sitting there. It would just count 1, 2, 3, 4. That's what this I is doing by itself. The example would be like 1 plus 2 plus 3 plus 4 plus 5 plus 6. That would be I equals 1 to 6. So in this case right here, my n in the example is 6, right? So this is telling me that instead of doing the numbers separately, I can just take the summation and do n times n plus 1 divided by 2, and I'll get the sum. So test it out. 6 plus 1 is 7, divided by 2 gives me 21. And sure enough, 1 plus 2 plus 3 plus 4 plus 5 plus 6 does actually equal 21. The way that you can test this out, incidentally, the way that this particular one is created, when it's counting numbers like that, you can add in shells. 1 plus 6 is 7, 2 plus 5 is 7, and 3 plus 4 is also 7. 7 times 3 is 21. That's actually how this particular one is made. That's not how they're all made, but this particular one, they do it in shells like that from the list. Okay, if you want to sum the squares of a list of whole numbers, right? So from 1 to whatever, and I'm going to square them and then sum them up, right? So 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, right? That would be 1 plus 4 plus 9 plus 16 plus 25. This is telling me that I could do n plus 1, 2n plus 1 divided by 6, and it will give me the correct sum. And sure enough, here my highest number n is 5. Notice I started at 1. That's important. Starting at 1, counting up. Right? Same thing here. Starting at 1, counting up. 5 is my highest n. So I have n plus 1, 5 plus 1. And then 2 times 5 plus 1, right? 2 times 5 plus 1 is 11. So 5 times 6 times 11 over 6 is 55. And that's exactly what this sums up to be, right? 25, 16, 9, that's 50 right there. And then 4 and 1 is 5, 55. All right, same thing but with cubes. And again, let me stress this. Do you notice up here they were generic, A to B, A to B. These are specific, 1 to some cap number. They must start at 1 for these particular formulas to work. Well, what if I want to do from some other number to another? Well, then you'll have to do from 1 to the first one and 1 to the other one and then subtract. That's actually how you would have to do one of those. Okay? So for these formulas to work, you have to be starting at 1. Technically, you could also start at 0 because plus 0 doesn't do anything. But typically, 1 is the counter. 0 on these particular formulas just doesn't add anything. Okay? But for the cubes, if I want to add 1 cube, 2 cube, 3 cube, 4 cube, 5 cube, 6 cube, and 7 cube, if I want to add all those cubes up, then notice, look, it's that same formula from up here, n plus 1 over 2. But now it's squared. Okay? So 1 cubed, 2 cubed, 3 cubed, that's 1 plus 8 plus 27 plus 64 plus 125 plus 216 plus 343. Add up all those hundreds of numbers, right? You're going to get 784. What I did was I said 7 was my cap number, n. So 7 plus 1 divided by 2, right? That's 7 times 4 is 28, but squared is 784. Okay? So what I have here are just some properties that will help us in simplifying larger summations. Okay? The examples we did in the last scene were really small summations because they were just a few terms here and there. But some of our summations may have 10, 20, 30, 100 terms to add up. I don't want to write that out, right? I got to have a more efficient way of doing that. So these properties are going to help me do that. Let's go through these, right? Now you've already seen the answers to these sums. Let's get them the other way now. Okay, so right here, starting with n equals 0 to 4, I'm starting with the fact that I see this plus right here, right? And that's like this one right here. I have two different expressions inside of one summation. I can split it into a summation for each one. Okay, so here that would be the sum from n equals 0 to 4 of 3n plus the sum from n equals 0 to 4 of 7. Now, if you remember from the last scene, if I have something that's just a multiplied number, right? Now I can actually take this multiplied number and bring it out front. In other words, I can multiply it after I'm done with the sum, right? That's one of our properties. I know it's not on the list here. That was the one I demonstrated in the last scene. If I have a multiplied number, notice I could not do that here because they don't both have the multiplied number. But now that I've split it, this one by itself has just a multiplied number, which I can bring out. Okay? Kind of like with derivatives, right? And antiderivatives. If there's that multiplied number, you can sort of bring it out and let it wait and come along for the ride. Same idea. I can bring the multiplied number out. Okay. So according to our formulas here, this should be 3 times. This is adding up from n equals 0 to 4. That's going to work for this. It'll be okay. Because remember what I said, it had to be 1 to some number, right? But 0 plus something is not going to do anything, right? It's not going to add anything. So I can still use the formula here. It can be 1 or 0 for these three to work. Typically we like 1, but 0 doesn't add anything. So right here, I'll have 4 times 5 over 2. Okay, because that's the number to the 1 power, and there's my counter is the same as that. And my maximum is 4. So 4 is my high number here. Then 4 plus 1 and over 2. Plus, that's this plus here. 7 is a constant. And I'm going from 0 to 4. So that's going to be 4 minus 0 plus 1 times 7. All right. So let's figure this out. I've got 4 over 2, which is 2, times 5, which is 10, times 3, which is 30, plus 4 plus 1 is 5, times 7 is 35, and we're getting 65, right? Which is the same thing that we got before, but this, with a little bit of practice, is considerably less work, right? Borderline in this case. I know we only had 5 terms, but it's still a good bit less work. Okay, here, from 8 to 11, I squared minus 1. Again, I see that it's 2 pieces and I can split them. So this is going to be summation I equals 8 to 11 of I squared minus the summation I equals 8 to 11 of 1. All right. So from here, what I need to do is notice that this is not 1, is it? No, it isn't. So I can't use this formula in its raw form yet. Okay? I'm going to get this guy out of the way first, right? This calculation right here is equal to 11 minus 8 plus 1 times 1, right? Because 1 is a constant. So I've got 3 plus 1 is 4 times 1 is 4, right? So I've got the 4, and it's actually minus, right? I'll go ahead and write that in. Minus 4. Because I'll include the whole thing. Okay, so how do I go from 8 to 11 when I really need the I squared to be from 1, well, to 11, whatever our max number is here, right? Okay, this is what I do. I'm going to rewrite this piece right here, this piece. I'm going to rewrite it as the sum from I equals 1 to 11 of I squared minus the sum from I equals 1 to 7 of I squared. Think about that for a second. It's the same thing that we were saying over here. If I want to get a part of a summation, it can be the same thing as 2 different ones that have been subtracted with butting up endpoints, right? So if I just want from 8 to 11, but the only way I can calculate it is from 1 to something, then I'm going to go from 1 to 11, get the whole list. And then I'm going to subtract out the pieces that I don't want from 1 to 7. And notice both of those will work in our formula because they both start with 1. Okay? So then for this guy right here, that's just going to be equal to 11 is the first cap that I have, so that's 11 times 12 times 2 times 11 plus 1 over 6, right? So that's 22 plus 1 is 23 over 6. Minus, now do the cap of 7, so that would be 7, 8, and 2 times 7 plus 1 is 15 over 6, right? Okay. So now let's see what I can reduce. Very quickly and easily, I can take the 6 into the 12, and that leaves me with a 2. And then right here, I can split the 6 into a 2 times 3. The 2 will go into the 8, leaving me with a 4. And the 3 will go into the 15, leaving me a 5. Okay, so let's multiply these out. I've got 11 times 2 times 23. That's going to be 253 times 2. 253 is 506. So this is 506. Take away 7 times 4 times 5. That's 140. Right? So then 50 minus 14 is 36. So I'm getting 366 from this. Okay? From adding up these two. And yeah, I'm going to admit, at this point, this was more work than the last time. Nothing's perfect, right? I have to be able to make it fit my formulas. If this cap right here had been 11,000 though, and I was going from 8 to that, this certainly would have been a lot less work than adding up thousands of numbers. At this point, it seems like a lot, but it never becomes more than this. The only reason I had to double up was because I needed to be able to change that under cap of 8 by subtracting off 1 to 7. Okay, now let's combine it together to get the final answer here. 366 minus 4 is 362, which is what we got before. Okay? So there are ways to use other formulas here to do these things. Okay, so look here, this one. I want to do from j equals 1 to 20, and I want to sum up all the terms of j to the third plus 5j squared. I mean, there's 21 things that I'm adding here now. This is starting to get to the point where I really don't want to write out 21 calculated different things if I can help it. So I'm going to do this the more efficient way. I'm going to split this up into the summation from j equals 1 to 20 of j cubed plus 5 times the summation from j equals 1 to 20 of j squared. Remember, it was a multiplied number for this one, so I was able to bring the 5 out. Okay, they both start at 1, so I can immediately use the formulas here. J cubed with 20 as my cap is going to be 20, 21 over 2, and then that whole thing squared. Plus 5 times 20 is my cap with the squared. That's going to be 20, 21, and 41 over 6. So let's see what I can do here. This is going to be 10 times 21 squared. So this is going to be 210 squared. Plus, I can reduce here the 6 into a 2 times 3. 2 is going to go into 20, leaving me 10. 3 is going to go into 21, leaving me 7. So essentially what I have here is 5 times, let's see, 7 times 41 is going to be 287, so 2870. 58,450. And I'm sure your other argument is, well, you just used a calculator. Couldn't I have just done that with the 21 terms? Sure. That still would have been a lot more work to be able to write out all 21 terms and compute them. Then after you've computed the 21 terms, add them all up. It would have been a lot more punching, a lot more work than what I've just done here, okay? Then I have to argue the next case. What about if I had 100 terms? What if I had 1,000 terms? What if I had a generic number of terms that I then want to take a limit and let that limit go to infinity? That's actually what we're going to be doing, okay? So I do need a generic way of representing these sums without actual numbers. And we have that, you see. Okay, and then these eventually I can have inside of summations that I throw limits on as well. We do need to at some point take limits of these summations. In fact, I'll have an example of that at the very end of this lecture. Okay, so you need to know these properties. You need to know how to split up the summations to make the sums more efficient, but also later on so that we can work these things a little bit more generically. Okay, now we want to actually start talking about what the title of this lecture was, Approximating Areas. What we're going to be doing is trying to figure out a close approximation to an area that's not easy to find. I have one example of an area that would be easy, that we already have a formula for, but we're not going to use the formula. And one area that we do not have a formula for, that would not be easy with conventional ways and methods. Okay? What we're going to do is we're going to try and fit nice and simple rectangles underneath the curves, and we're going to try and see how fitting these in there can be a close approximation, but you can still see the error in them. And then I'll show you some ways to try and improve the approximations. And then finally, in the next scene, we'll use limits to get the exact values of these areas. Okay, so let's start with the easier one right here. What we have is the function g of x is equal to 5 minus 2x, right? This line right here. And what I want to do is I want to approximate the area underneath this line between -1 and +2. And I'm going to do it with 3 rectangles, okay? So in other words, 3 strips that I'm going to put underneath the curve, and I'm going to try and see if I can calculate the, well, not try and see, I'm going to calculate the areas of these rectangles and then add them up and see how well we can approximate the area under here. Okay? Every time you do this, with when you have a certain number of rectangles, you have a choice. You can count your rectangles from the left-hand side. That's what we call the left-hand sum, or you can just say left-hand side. You can also choose to count your rectangles from the right-hand side. Okay? So what does that mean? When you're creating your rectangles, okay, you can count the height of the rectangle on the left side or on the right side of the rectangle, okay? And it does make a difference because the height of the rectangle is going to be the distance from the axis up to the function. So if I pick, different sides of the rectangle, I'll be picking different y values for the heights. So one rectangle is going to be taller than the other one. And so it does actually matter. But whichever one you pick, you stick with that decision for all of the rectangles. And we get either an over approximation or an under approximation. Okay? Let me draw out the left-hand sum for this one so that you can see what it is I'm referring to. Okay? So the left-hand sum on this one, if I'm starting at -1, what that means is I'm going to fit in some rectangles here. The first one being at -1 on the left-hand side. So I have this rectangle, and then I would come straight across, right? And then I'm going to come down right here, along here. Okay, so then I've got this rectangle here. Side question. How did I know how wide to make that rectangle? That's a really good question, Mr. Simon. You just jumped right in and drew a rectangle. We don't even know how you knew. Well, I knew that I was starting at -1, right? So I drew the height from -1 up to the graph. And then I kept that height all the way across. And how did I know how far across to go? The width of your rectangle, we call it delta x, is b minus a over n. Okay? So right here, the delta x for my graph right here, delta x is 2 minus -1 over 3. 3 is the number of rectangles. That's the n that I'm using here. Okay? So I have 2 plus 1 is 3 over 3 is 1. So right now I'm using a delta x, a rectangle width of 1. And notice that's exactly what just happened right here. The width of this rectangle right here from here to here is 1. Okay? Again, I'm going to draw the next rectangle with a left-handed idea. So my next rectangle starts at x equals 0 right here. And notice the height of that hits right here. And I'm going to make a width of 1. So that means I'll draw up to here. Like this. Like this. Notice where the height is, right? The height of this rectangle is lined up with the left-hand side, the left-hand corner of this rectangle is hitting the actual function there, right? So then I'm going to take the area of this rectangle here. And then one more, we're doing 3 rectangles, right? So I'm going to draw up to here. Remember, each of these are a width of 1, 1, and 1. And I've got this rectangle here. Again, how did I know that this was the left hand? Because I'm using the left side of this rectangle right here being the side that hits the function. What I want you to notice is my rectangles are covering more area than the area that I wanted underneath the curve, right? I wanted to approximate the area that was underneath this line, okay? So this is where the function is right here. And I'm trying to approximate under this, the area under this, but above the axis between -1 and 2, okay? So you'll notice that my rectangles are above. It's an over approximation. Notice this is a decreasing function on this interval, okay? And the left-hand sum on a decreasing interval will be an over approximation. So if you know for a fact that your entire interval is decreasing and you choose left-handed side of your rectangles for your sum, then you will have an over approximation. Now wait a minute, you keep saying side and sum as if they're interchangeable. Yes. Let's actually calculate this thing now. Look, the left-handed side, the left-handed sum here is going to be the addition of the 3 areas of the rectangles, right? So that's going to be rectangle area 1 plus rectangle area 2 plus rectangle area 3. Now how do I do the area of a rectangle? That's just the width times the height, right? Okay. For rectangle number 1, the width is 1. So 1 times, what's the height here? Well, it's the distance from the axis up to the function. Or in other words, the y value, right, of the function at -1. So that's g of -1. That's this height right here. Plus, what's the area of rectangle number 2? That would be 1, because it's the width, times the height of rectangle number 2. Notice I used x equals 0, right? Right here. So that's g of 0 plus 1 times, because the next width is 1, g of 1. Now I just need you to realize how I'm setting up width times height, width times height, width times height, right? And they're all with 1. So I really could have just written this as 1 times, because I could just, factor out that width. And it's g of -1 plus g of 0 plus g of 1, right? I could have just done that. That would have been easier to write down. But I wanted you to see how I was doing the individual rectangles there. But most of the time when we're doing these, you'll see that what I'll do is I'll factor out the width, because they're all multiplied by the same width here. We're always going to be choosing the same width of all of our rectangles, delta x. Okay? So the width is out here, and then really what I'm doing is just adding up these function values, right? Now wait a minute, we were supposed to be going from -1 to 2. Why don't I see g of 2? Remember, I'm doing 3 rectangles, and I started at the left-hand side, right? If you count the left-hand sides, right, I'm starting at -1, and I'm only doing 3 rectangles. So g of -1, g of 0, g of 1. And then the 2 just happens to be where the last rectangle ends. But I didn't actually use g of 2. Look, g of 2 would be this little bitty height right here, right? Okay, so now I can actually add that up. That's going to be 1 times g of -1. That's 5 plus 2, which is 7, plus g of 0, which is 5, plus g of 1, which is 3. So my left-handed side sum of the rectangles here is going to be 1 times 7 plus 5 plus 3. So that's 15 total. Okay, now remember, that's an over approximation. Okay, I know that because I'm on a decreasing interval and it's the left-hand sum, right? Remember, from left to right, if it's decreasing, then the left side is always going to be bigger than the right side. So that's why a left-hand sum will be an over approximation, okay? Because I'm picking the bigger value as it goes down. Let's do the right-hand sum. Again, the width is still 1, right? But then how do I actually draw my right-handed sum rectangles? Okay, so my interval starts at -1 right here, yeah? But I want to use the right-hand side. So I'm not going to start counting until 0 right here. So that means my first rectangle has to have a height that's the same as at 0 right here, which means I'm just going to do this. That's going to be the left-hand side, the right-hand side's rectangle, because the right-hand side of the rectangle is meeting up with the function here. Next, do the next right-hand side will be at 1. That would be right here. That would just be this. Notice it caps off right here, right where it meets the function on the right-hand side of that rectangle. And then lastly, my last right-hand side is here at 2, which is right here. So that's the height of this rectangle, which will go to here. Okay? So notice all of these right-handed rectangles. And again, that's because the right-hand side of the rectangle is connecting with the function. Remember, that's how we count this. The side that you're saying is the side of each rectangle that meets the function. Okay? Incidentally, there's also midpoint, where you can pick the middle to meet the function. There's all kinds of choices. We typically just do left and right, though. Notice the left-hand sum, the right-hand sum here is underneath each time. I have this little gap under the curve where the right-handed side rectangles are not getting quite up to it. So the right-hand sum is going to be an under approximation. Okay? All right. So right here, the right-hand sum is going to be 1, the width, times, remember, it's actually 1 times all of them, but I'm just factoring out the width. And this time it's going to be g of 0 plus g of 1 plus g of 2. Because I'm picking the right-handed x values of each one on the right-hand side of each one of those. Okay? So, now I'm going to add these up. This is going to be g of 0, right? Still the same as before, that's 5, plus g of 2, which is, whoops, not g of 2, g of 1. Boo, I skipped over it. I was throwing myself off. 3 plus g of 2, which is 1, right? So 1 times 5 plus 3 plus 1. I'm going to get 9. Okay? So I've got two approximations to the area here, the left-hand sum and the right-hand sum. One other thing that you may not get asked often is to increase the approximation of this, you can actually take the average of these two, because I can see that one of them is purely overestimation and the other one is purely underestimation. So a lot of times what I'll do to increase my estimation on these two methods is to take the average of them. Okay, so if I take the average of these two, right, I call it the mean approximation. The average of them, 15 plus 9 is 24, divided by 2 is 12. Okay, so all of those are good approximations. Well, decent, right? 12 is probably a really good approximation, if not right on top of it. But 15 and 9 are not bad approximations. Now let's try the other one. I have the function 1/4 x squared plus 1 on the interval from 1 to 4. And we want to do 6 rectangles this time. All right. So first things first, let's figure out the width of one of the rectangles so that I know how far to count each time. Okay, so my delta x this time is 4 minus 1 divided by 6, because it's end minus beginning over number of rectangles, which gives me 3 over 6, which is 1/2. So my width of a rectangle is 1/2. Okay, so to get 6 rectangles out of here, that means I'm going to have to slice rectangles here, 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 here. And technically the last one could end up here, right? All right, so let's start with the left-hand sum, the left-hand side rectangular sum. To do the left-hand side, I'm starting with the first number, because the first number is the leftmost. So I'll be drawing my rectangle up to here, right here where it meets the function, and then I'll be drawing it across, and then back down again. So there's my first rectangle right there with a width of 1/2. Notice the rectangle's left-hand side meets up with the function. Okay? So this is my first left-hand side rectangle right here. Next, I'm at 1.5, and I'm going to follow that all the way up to the function here. And then that's going to come across and finish my rectangle. So here's my next rectangle, right? Again, a width of 1/2. Then I'm at 2, right? I'll go up, and then I have a width of 1/2. Again, keep in mind that it's the left-hand side. I'm on 2.5 now. I'm hitting 2.5, and the function value now is the height here, coming across, back down. Still have a 1/2 and a 1/2. Right, here's this rectangle. Now I'm at 3, right, where 3 meets the function, come across a 1/2. It's getting kind of tall. I'm going to have to start straight edging it. Probably should have been the whole time. I'm going to draw this line all the way up to the top first. Right. Okay. So here's the rectangle associated with x equals 3 on the left. See? 3 is on the left of this rectangle, and it hits the function there. I have one more rectangle. It's the 3.5, right? Because I went a 1/2 here, and I have one more 1/2 to go. And it's coming across here. and down like this, right? So here is my left-hand side approximation, my left-hand sum. Notice, because this is an increasing interval, all of my left-handed rectangles are underneath, because using the left is using the lesser function value, right? Okay. So now we want to actually do the left-hand sum. Okay? Notice all of my widths are 1/2. So technically, I should be doing 1/2 times f of 1 plus 1/2 times f of 1.5 plus 1/2 times f of 2 plus 1/2 times f of 2.5 plus 1/2 times f of 3 and plus 1/2 times f of 3.5. Notice again, I'm not using f of 4. Give it a count, right? 1, 2, 3, 4, 5, 6. 6 rectangles. 4 is not being used because 4 is not on the left of any rectangle. There's no rectangle over here for 4 to be the left of. So I will not be doing f of 4 for the left-handed sum, right? Okay, so just like before, remember they all have that same width of 1/2. So I'll be factoring that out. And then I'll just need to start figuring out, okay, what's f of 1? What's f of 1.5? What's f of 2? What's f of 2.5? So on and so on. F of 1, right? I'm going to have 1 squared times a fourth, which is a fourth, plus 1. So that's going to be 1/4 plus 1 is 5/4. Okay. Plus f of 1.5, that's 3/2. Squared is 9/4. That makes 9/16. So 25/16. Okay, that's when I plug in 1.5. Plus f of 2. 2 squared is 4 over 4 is 1 plus 1 is 2. Plus f of 2.5, that's 5 over 2. Squared is 25 over 4. So 25 over 16, 41 over 16. Okay. F of 3. 3 squared is 9. 9 over 4 plus 1 is 9 over 4 plus 4 over 4, which is going to be 13 over 4. Plus f of 3.5. That's 7 over 2. So that's 49 over 4 times 1 over 4 is 49 over 16. So 49 over 16 plus 16 over 16. 49 plus 16 is 65 over 16. Okay, so let's recap what I've just done. I took the 1/2 out of all of these multiplications, right? Because these are the areas of each of those little rectangles. I'm using the function values as the height, but the ones on the left only. And then each one was a width of 1/2. Then I factored out the 1/2, and then I just plugged in the function value for each one. So these are the different heights on the left-hand side of each of those rectangles. And now we just need to add them all up. Okay, so it looks to me like a common denominator of 16. So I've got 1/2 times a big bunch of numbers over 16. Let's see, that's going to be 20 over 16 because it's times 4, plus 25, plus 32, because 16 times 2, right? 41 was already there. Times 4 is plus 52. And then already at 16 is 65. Okay, now lucky for us, the 1/2 with the 16 is just going to give me a denominator of 32. Right, that'll be easy for the denominator. Now let's add up here. That's 45, 86, 110, 118, 170, 235. Right. Okay. So 235 over 32 will do just fine, because 32 is just 2 to the 5th power. It's nothing but 2's, and none of those are going to go into 235. 235 is just 5 times 47 anyway, so that wouldn't have worked out. Okay, so that was using all the left-hand sides. Okay, now let's talk about the right-hand sides. Right, the right-hand sides are going to be the same positionings of the rectangles. Okay, I'm not moving any of the rectangles. It's just that for each rectangle, I'm going to be focusing on the right-hand side. So for the first rectangle, I don't use 1 for the right-hand sum. I'm going to start with the next number, because 1 is not on the right of any rectangle. On the right of the rectangle is 1.5. Okay, so that's up to here. This is this rectangle right here, and it's going to come across like this. So this rectangle is here. Next, I go to 2 is on the right hand side of this one. Okay, next is here on, this is the right hand side, so it's above here. Okay, remember what I'm doing is I'm just looking at each of these rectangles and I'm fading over to the right hand side of it and using whatever that right side is as the height of everything to the left of it. So right here, this is the right hand side of that rectangle right here, and so I come over, and this has to be that rectangle right here. Okay, next rectangle, this would be the height of it right here on the right hand side. Just like that. And that means it would come across to here. And then one more, right? I still have this last rectangle. The right hand side is at x equals 4, which comes all the way up to here. And then this would be that rectangle. So those rectangles are on top of each other because they're occupying the same x values. But using the right hand side of each one of them gives me a higher y value for the whole rectangle. So you'll notice when something is increasing, the right hand side is an over approximation. Okay, the right hand sum using the right hand side of each one of these rectangles is going to over approximate when doing an increasing interval. Okay, you'll notice we had purely decreasing last time, purely increasing this time, so that I could demonstrate that to you. If you have a mixture, you really got to graph it out and look. And even then, you may not be able to totally tell. But if you can do a 100% increasing or 100% decreasing, you'll know right away which one of these is an over and which one of these is an under, depending on the type of interval you have. Okay, so I'm taking the right hand sum now, and it's going to be an over approximation. This is how I set up the left hand sum, right? Well, notice the only difference is I'm still going to use f of 1.5 right there. It's this height. Okay, oh, I'm sorry, no, this height. And 2 is here, this height. 2.5 is this height. 3 is this height. 3.5 is this one. And then I'll be using 4 for the last one. So I won't be using 1, and I will be using 4. Okay, so that's the only difference there. I'm going to have 1/2 times f of 1.5, 2, 2.5, 3, 3.5, and 4. So those are the right sides now. Luckily for us, we've already done most of these calculations, right? I won't be using the 5/4. I'm going to start here. F of 1.5 is 25 over 16 to 41 over 16, 13 over 4, 65 over 16 is F of 3.5. Let's do F of 4. 4 squared is 16, times a fourth is 4, plus 1 is 5. All right, so let's finish it up. I have 1/2 times, and I know it's going to be a big bunch of numbers over 16, common denominator. We've already done most of them. I won't be using the first one, so I go straight with the 25, 32, 41, 52, 65, and then we have one more, right? 5 times 16, 50 and 30 is 80. Okay, so a total gain of 60 gives me 295 over 32. So I have an over approximation here for this one, right? And an under approximation for this one, right? Now, of course, if you do both approximations without graphing it, you can pretty much guess, as long as all of your arithmetic is spot on, the larger one is going to be an over approximation and the smaller one is going to be an under approximation. I mean, that's not going to be guaranteed always true, but it's you know, a pretty safe guess most of the time. But if you have a totally increasing or a totally decreasing, like all the time, you'll know for a fact. Left-hand side on an increasing is an under. Right-hand side on an increasing is an over. Things like that. Like I said, now for me personally, if I want to get a better approximation, what I'll do is I'll average the two. Okay? So they're both over 32. That's going to be easy to do. The mean approximation here, it's going to be over 32, right? So really all I'm doing is averaging the 295 and the 235, which, oh, okay, we can do that one visibly. So there's a difference of 60 between them. Cut the difference in half, 30 would give me 265 over 32. Right? So the mean approximation we're guessing is somewhere in the neighborhood of 265 over 32. All right? So this is how you do a left-hand sum and a right-hand sum approximate area under a curve using rectangles. Okay? You'll be told usually how many rectangles, either by your situation or just by the problem. Once you know how many rectangles, you divide up your interval by calculating delta x. Okay? Then you can divide it up. All right. Then once you do that, don't forget that what you're doing is the area of a bunch of these rectangles, and the width is always delta x. The height is always the function value, either to the left or to the right of your rectangle, depending on which one you're doing. And then you just need to know when you have an over and under approximations. Like I said, this bit is extra that I like to do whenever I'm approximating these, because it usually is a pretty good approximation when you just average the two together. With something linear, it gets right on top of it, if not equal to it. But with things that are non-linear, of course it won't be exactly equal, because the amount that this is over is not equal to the amount that the other side is under, right? Or same thing here and here. The amount over is not the same as the amount under. It's not symmetric anymore because it's not a straight line anymore, right? But mean approximation is a good way to get closer than either one of these two by themselves. All right? Okay, so now in the next scene, let's take a look at how can I try to get these 100% accurate. All right, let's do these same two problems again to wrap up this conversation, but let's do them so that I can get the actual areas here. And I'm going to need the help of some limits to do it. Also the help of all that summation stuff that we did at the beginning. Okay, so here's the idea. I was using rectangles underneath the function to approximate it, right? There was still, for the blue rectangles here, you can see there was still some gap underneath of it, right? Okay, so here's what we have. Whenever I have a certain number of rectangles, I have these gaps, right? But what happens if I increase the number of rectangles? I'm not changing the whole width here. I'm still going from -1 to 2. But if I increase my number of rectangles, like for example, there were 3 here, right? What if I were to increase it to 6? If I increase to 6 rectangles, then from the underneath, I would get something that looks like this. I would get this rectangle slicing through the middle here. I would get this rectangle slicing through the middle here, like this. And I would get this rectangle slicing through the middle here, like this. And then all of my widths wouldn't be 1 anymore. They would each be a half now, right? If I did 6 rectangles, then my width of each little bitty one would have been a half. And now notice the gap above each small rectangle is less error total. Well, what if I went from 6 to 12, right, and cut it in half again so that the width of each of these was a quarter, right? If I were to cut it in half again and fill in that much now, right? Now there's 2 very small pieces in there. Same thing here, same thing here, same thing here, and here, right? So the more rectangles I keep slicing, I don't change the width of my entire interval. I'm just slicing it up more and more and more. So what's the maximum number of rectangles? Infinity, of course. Wait a minute. Infinity is not a number that we can actually obtain, though. Was that a goal that I set too high? No, no, no. That's where limits come in. So here's what I need to do. I need to set up something with a generic number of rectangles, n. Okay? So if I can set up something with a generic number of rectangles and then just let that n go to infinity, then it should tell me what happens if I were actually able to slice this up with an infinite number of rectangles. Okay? It would show me the pattern as n goes to infinity, and I would see what the actual area is. Let's do this in stages, okay? First, let's set up the way it was before with the 3 blue rectangles, but let me set it up in a summation kind of way. All right? So watch. If we still do the 3 rectangles, here, let me make some space right here. If I still do the 3 rectangles, then my delta x is going to be equal to 2 minus -1 over 3, which gives me 1, right? Okay. And what do I want to do? I want to add up, so sum, all of the areas of these rectangles, right? And remember, the area of the rectangles are the function heights that I use as the height of the rectangle times the delta x that we use. So the only thing I need to know here is if I'm going to number this summation like with an I, right? Let's say I let I go from 1 to 3. Well, that should make sense, right? Because I'm doing 3 rectangles. Okay? Then I just need to put, this is the way they symbolize it right here. They put x sub I. I need to have my x values based on some iteration of I. So here's what we do. What's my first number? My first number is -1. Okay, so here's the way that we number these things. X1 should be -1, right? X2 should be 1 up, that would be 0 because I'm adding plus delta x, right? From x1 to x2. So that's from here to here. Then I need to do it again. I need to go another delta x. So if I add delta x again, x3 would be 1. Okay? And notice that's the same thing we did before. We did f of -1, we did f of 0, and we did f of 1. That was the left-hand sum, you remember? Okay? So I just need a way to put these three things in a pattern with an I. Okay? So here's what you do. You notice we have a starting point, right? We have a starting point, and then I get to add from that starting point to get to the next one. And then from there, I add again to get to the next one. So it seems to me like we just need to keep track of where we started and how many of these jumps we need to make to get to the next one, right? So x sub I, in this case, is going to start at -1, and then I just need to add some number of jumps. So it's going to be something like I times delta x. I will then tell me how many times I'm going to jump. And actually, the numbering on this is a little bit off. If I do I times delta x, I actually need to make this x sub 0, 1, and 2. And I would need to let I go from 0 to 2. Think about that for a second. I'm using the little subscript on the x to denote how many jumps have you made. And at the beginning, I've made 0 jumps, right? So I is 0. But after 1 jump, I'm 1 delta x down. After 2 jumps, I'm 2 delta x's down, right? So watch. If I put in a value of I, like 2, then it would be -1, my starting point, plus 2 delta x jumps. You see? So I'm going to use I as a counter for how many rectangles have you jumped and moved on from. Okay? So I have my starting point, and then I'm just going to count delta x's. And I'll never go over the whole interval because delta x is divided specifically to add up. Okay? So that no matter what, it adds up to the correct one. All right? Let's try this again. Let's try numbering this again, but with the 6 rectangles, right? Let's try again. Let's see what happens if I do 6 rectangles, right? That means I would change this, and this, and this. And then I would have to renumber these again, okay? So if I'm doing 6 rectangles and I'm starting at 0, x0 is still -1, okay? My delta x, though, if I'm doing 6 rectangles, is going to be 1/2. For x sub 0 being -1, x1 would be -1 plus delta x, or in other words, plus 1/2. X sub 2 would be -1 plus 1/2 plus 1/2. Right? That would be like this. Here's my starting point. Here's 1/2. Here's another half. Okay? x3 would be -1 plus 3/2. x4 would be -1 plus 4/2. x5 would be -1 plus 5/2. 5 1/2 jumps. And notice that's 6 rectangles, right? Because I'm doing the left-hand side in this particular example. -1 is my starting point, and then I'm doing delta x jumps. 1 jump, 2 jumps, 3 jumps, 4 jumps, 5 jumps from the beginning. And then that's going to make it count along, okay? So if I picked 20 rectangles, I would count from x0 up to x19, right? Okay, fine. What if I wanted to do right-handed sums? Just as easy, okay? Instead of doing 0 to 5, this is a left-hand sum from 0 to 5. If I want to do a right-hand sum, I simply number the sigma differently. I would be 1 to 6 in this case, times delta x. Notice everything else is the same, right? I'm still plugging my x values into the function. But if it's the right-hand sum, I won't be using x0, right? I won't be using that one because that's a left-hand side. But I will be using this. That's my first right-hand side of the second one, third one, fourth one, fifth one. And then I would just have to go to x sub 6, which would be -1 plus 6 halves. Now notice 6 halves is 3. 3 minus 1 is 2, which is the other side, right? So this does actually equal out to 2 like it's supposed to. Okay? So left-hand sum just means that I start at 0 jumps, and I is counting the number of jumps here, right? Right-hand rule says I start with 1 jump as my first number, and then I count up to the last other side. Okay? So it's all in the way I'm using the delta x to number one rectangle after another. So how would I write this out for a generic number of rectangles? All right, so here we go. Generic number of rectangles. In other words, let's say n rectangles. My delta x would still be 2 minus -1, but it would be over n. So delta x would be 3 over n. Okay? So what would my x0 be? Well, that'd still be -1. That's still the left-hand side. What would x1 be? That would be -1 plus whatever 3 over n is, because I'm doing 1 jump. What would x2 be? It'd be -1 plus 2 jumps of 3 over n. Okay? What would x sub 7 be? -1 plus 7 jumps, if there happen to be that many, if n is big enough to permit that. Okay? So then let's get generic. What would x sub I be? In other words, what is the ith x value in the split? That would be -1, my starting point, plus I number of jumps. And 3 over n is still the size of my jump. Okay? So that's what I need to keep in mind. Every time I set up one of these things, this is how I number my x values. Okay? I have my starting point on the left, and then I do a generic variable or a counter times whatever the width of the rectangle is, the delta x. So I'm going to write that right here. X sub I is -1 plus I times 3 over n. Okay? So now let's do some actual calculations with it. Remember, if I'm going to do one of my sums, like let's say I want to do the right-hand sum. Okay? The right-hand sum is going to be, if I add up, right? Add up. Let my I be my counter from 1 to how many rectangles? N. It would be n number of counts, right? And then I have to do the function of the x values, x sub I, times the delta x. Right? Because each one of these is a height times a width. All I'm doing is I'm adding up rectangle areas. Okay? And what makes the difference is every time I counts up, I get a different x value to plug into the function. Right? Okay. So we actually know what all of this stuff is, and this shouldn't actually be f of x. I made a boo-boo. This should be g of x. Sorry. Right? G is the heights here times the delta x. Okay, now that's just the right-hand sum though. What I have now is a generic setup for the right-hand sum. let's go ahead and see what it looks like when I plug in the delta x's and the x sub i's. So I have the sum I equals 1 to n. G of x, that's 5 minus 2 times x. So 5 minus 2 times, what was x? X sub I was this. -1 plus I times 3 over n. And then times delta x, which is times 3 over n. Okay? Now I know it looks a little bit complicated, but we can simplify this stuff down, do some distributive properties, combine all the like terms that we can. Okay, it doesn't have to look that complicated all the time. Just make sure you're with me on the setup, right? G is the function, right? 5 minus 2 times an x. And then our x values have been listed and enumerated with I this way by counting the number of jumps starting at -1. And it's in the summation using that counter. So this is actually going to sum up all of those different heights times the width, delta x. Okay, there's only one piece missing. This is the generic setup right here. This is waiting for some n to be picked. If I have this set up, by the way, and you just pick n equals 3, the answer that would drop out of this would be the one that we computed earlier, okay, for the right-hand sum. So here's what I need to do, though. I don't want just any number of rectangles, because remember, some numbers are still going to have errors. I want to let n be as big as possible. So the only thing left to do is to have a limit. I want to let n go to infinity. And then that will complete this calculation. I can figure it out, and we'll get the actual area for this. Okay? So watch. Instead of a right-hand sum, as soon as I put a limit on this, it's not just a right-handed sum anymore. If you let n go to infinity, what you are doing is you are now taking every single y value and just adding up each y value. Because letting n go to infinity means that you actually get to an infinitesimal width, right? I'll be dividing by something going to infinity here as my width of my rectangles, okay? By infinitesimal, what we mean is the width of a point. It technically still has width. I can't say that it equals 0, because then that would zero out my whole area, and that wouldn't be right. It's infinitesimal width, okay? Which is basically the width of a single point. And all you're doing then after that is you're summing up the function values. That's all you're doing. Think about it. The area would be perfect if you could just sit there and stack y value after y value after y value next to each other, and it would fit perfectly underneath the curve, because the curve is created with those y values. That's what we're doing here. By letting n go to infinity, we're taking and turning this into just a sum of y values. So let's do that. Now, instead of a right-hand sum, that's not what this is going to be anymore. Okay? I want you to remember that our approximate area there was 12. I'm going to make some room for myself. And now I'm just going to say that the area is equal to the limit as n goes to infinity of this. Okay? Now it's complete. What we need to do now is actually do the calculation. So let's start by simplifying this mess up in here, right? Let's say it's equal to, I got my limit. That limit's not going to go anywhere. N is going to infinity. I got my sum. That's not going anywhere, just pretty much copying it for now while I simplify the stuff. Okay, so then what I'm going to do is I'm going to distribute this -2 in here. And that's going to give me 5 plus 2, right? And then minus 6i over n. Because notice, I could really just do the I times 3 here. And then the -2 multiplies in there as well. and it's still times 3 over n on the outside of each y value. Okay, I can do one more thing, right? I can still combine these. And here's the other thing. Do you notice this is a multiplied 3 over n, just kind of times the whole thing? 3 and n have no dependence on I, which is the counter of my summation. And remember what we can do with multiplied just numbers on a sigma. I can bring those out, right? So watch, this is what I can convert this into. The limit as n goes to infinity, and then the 3 over n is outside of the sigma. I equals 1 to n. And then here I've got just 7 minus 6i over n, like that. Well, now it should look a little bit more familiar to you from the sigmas that we did earlier, right? I can actually start to break this down into separate sigmas and take all of the pieces out and try to just simplify each individual piece with those properties and rules that we have. And this is the main reason why we wanted to practice those, because I can do things generically with the sum of just a number and the sum with just an I. We have formulas for all of those things. Then once all of that is done, I'll be able to perform the limit, because all of the n's will be scattered everywhere and all of the i's will be gone. So watch. Here, I'm going to split this up into limit n goes to infinity 3 over n times, and I've got the sum I equals 1 to n of 7 minus 6 over n summation I equals 1 to n of I. Okay, now look really close at that, and let's go through it again. This was just a number, right? So I left it the sum of just the number. Minus, I was able to split my sigma on like we did earlier. 6 over n times I would have been all by itself in this summation, but 6 over n is a multiplied number just for that one sigma. So I pulled it out, right? I can multiply it out front like we did earlier. And then look at what we've got. We have a formula exactly for that. From 1 to n of I to the 1, we have a formula for that. Also, a summation of a number, we have a formula for that too. Okay, let's keep going. I have limit as n goes to infinity. 3 over n is still there. And then remember the formula for this was n minus top minus bottom plus 1, right? So that's n minus 1 plus 1 times 7. Minus 6 over n times, and then the formula for the summation of I, remember, is you take the top number and the top number plus 1, divide by 2. So that's n plus 1 divided by 2, like that. Notice I've gotten rid of all my summations now because of the way I can add up the properties here. Let's simplify this out a little bit more. I get limit as n goes to infinity. I've got 3 over n times, that's just 7n, minus, notice right here I've got an n in the bottom and an n in the top. Those can cancel out, or reduce rather. And then also the 2 will go into the 6. That leaves me with negative 3 times n plus 1. Right? Okay, so here we go. We're almost there. I have limit as n goes to infinity. I've got 3 over n times 7n minus 3n is 4n, and then negative 3 times 1 is negative 3. Distribute the 3 over n into both of these. Okay? So then we're only one step away. N goes to infinity. 3 times 4 is 12. N over n, right, eliminates. I'm just left with the 12. 3 over n times negative 3 is negative 9 over n. And now I'm just going to take the limit. The limit of 12 is just 12 because there's no n in there. And the limit as n goes to infinity of something with an n in the denominator, this goes to 0. What am I left with? 12. Which is what we came up with as our approximate area, right? Remember what I told you, since it was a straight line, the average was going to balance out due to symmetry. So the 12 that we got earlier was actually equal to the area, even though it was the average approximation, right? But this is the real way that we use calculus in order to get an area under a curve. I know it seems like a lot of steps, but the more you practice, the more you do the setup and the build, you'll see it's the same steps every time, and it just becomes an old habit, right? You're always going to set up your function with the counter xi. You're always going to have your delta x. You're always going to simplify and split it up. And then you can use your sigma rules to break things down and then simplify until the limits get rid of all of the things that have n's and denominators. Okay? So we're going to do that same thing to this guy here. All right? Now this one is parabolic. Okay? So our approximation here is not going to be exact anymore, but it should be pretty close. To make some space, I'm just going to get rid of this. So let's go through this process again. I've got my function, right? I've got my interval, and I want to set it up for a generic number of rectangles, n rectangles, right? So for n rectangles, that means that my delta x is going to be 4 minus 1 over n, 3 over n. That's just a coincidence, by the way. I didn't mean to make both of them length 3. I just kind of randomly picked some numbers for these, but it's not always going to be 3 over n. It can be any number over n. It's whatever the width of your interval is over n, basically. Okay, and then I'm going to number my x, the number of cuts, right? Remember, the very first x here is positive 1 plus I times 3 over n. And it's times delta x is what it is. Okay? Whatever that delta x is, this is how you set up your xi. This is how I count my x's as I slice them. Right? As I make my rectangles, I always start on the left-hand side plus however many slices deep I want to go times how far each slice has to go, right? The delta x. Okay, so let's see. My area is going to be equal to the limit as n goes to infinity of the sum I equals 1 to n, because we're summing up all of the areas of n rectangles, and it's going to be f of x sub I times delta x. This is the formula you want to remember for calculating the area, okay? The function evaluated at the x's times the width of each rectangle, and I'm summing all of the rectangles. So what does that look like for this function with this x setup and this delta x? Limit as n goes to infinity, sum I equals 1 to n. My function is 1 over 4 x squared plus 1. So I put a bracket. 1 over 4, x is xi, that's this. So 1 plus 3i over n, I'll just make that easier on myself, right? 3i over n, squared, because x is squared, plus 1. This is my function with the x value representation plugged in, times delta x. In this case, again, that's 3 over n. All right? Okay, here we go. Next, what I'm going to do is I am going to take the 3 over n outside, and I'm actually going to play another cruel game too. See this 1? I'm going to take that as a 4 over 4. And all I'm doing is making this easier on myself. This is what I'm doing. See how I have this 1/4 here? I'm just kind of helping myself out. I'm going to pull the 1/4 out to make this look cleaner. But in order to do that, the 1/4 has to come out of everything in the bracket. So I just made this 4 over 4 instead of 1 so I can pull the 1/4. Okay, so I have limit as n goes to infinity. I'm going to have 3 over 4n summation I equals 1 to n. And the only thing that's left in here now is the 1 plus 3i over n squared plus 4, like that. Okay? Alrighty, so here I go. What I'm going to do is I'm going to FOIL this out and combine like terms. So limit n goes to infinity. I have 3 over 4n is still there. Still doing a summation. I equals 1 to n. And now what I have inside of my summation is going to be 1 times 1 plus the 4. So that's 5. Then I have 1 times 3i over n and 1 times 3i over n. That's going to give me a total 6i over n. Okay, make sure you're with me. All I'm doing is writing out the 1 plus 3i over n, right? Since it's squared, what I'm doing is I'm writing it out. 1 plus 3i over n times 1 plus 3i over n, right? So far I've done the 1 times 1 and added the extra 4. And I've done the 3i over n times 1 and the 3i over n times 1. So now there's just one thing left. I just need to multiply the two 3i over n terms. And that's going to give me 9i squared over n squared. Right? Because I'm just multiplying those. Okay. So next, I'm going to split up my sigma so that I can do each one of these with a separate formula. So I've still got my limit. N goes to infinity. I have 3 over 4n. And now I've got the big bracket. I'm going to have the sum of the number 5 plus, now look, 6 over n is a multiplied number with the I. So that's what I'm going to do. I'm going to have 6 over n times the sum with I. And then what's the next one? The constant is 9 over n squared. Right? And it's the sum with the I squared. Right? Okay, so now I'm going to perform each one of these formulas and rewrite it. So I've got my limit. Try to get that out of the way. I've got 3 over 4n times. That's just going to be 5 times n. Right? Because I've got n minus 1 plus 1, which is n times 5. That's the constant multiple one. Next, I've got 6 over n, and then that's actually the same piece we did over there, right? That's going to be plus 6 over n times n plus 1 over 2. Plus 9 over n squared times, now here I need the formula for the sum of the I squared. That's the n plus 1, 2n plus 1 all over 6. All right. We're almost done. let's simplify what we can. Notice the ends will eliminate there. 2 into 6 is going to leave me a 3 again. This n will take out the squared. Here the 6 and the 9 will reduce to a 2 and a 3 there. Okay? So let's see. I'm going to have the limit as n goes to infinity. I've got 3 over 4n times 5n plus 3n plus 3, right? Because that's just 3 times n and 3 times 1. Plus, now before I go any further, here's what I want to show you. What I've got right here is 3 over n, or 3 over 2n, right? Times, this n is gone, the 2n is here, so it's just these two things multiplied together. All right? Which, well, we could do this a couple of different ways, but let's go ahead and do it this way. I've got 3 over 2n times 2n squared, and then 2n and 1n makes 3n plus 1. Okay? I just want you to see that this is what we've got right here after we did all the reductions and everything. Okay? So what I'm going to do is I'm going to multiply the 3 over 2n times each one of these. All right, so 2n and 2n squared reduce, and it leaves me with just a 3n. 3 over 2n times 3n leaves me with a 9 over 2. And then anything times 1 is itself. 3 over 2n, right? Okay. So it looks to me like we can simplify and combine, right? 5n, 3n, 3n. And then I can also combine the 3 and the 9 halves there. So limit n goes to infinity. 3 over 4n times, I've got 11n. And then I've got 3 is 6 over 2 plus 9. So I've got plus 15 over 2 plus 3 over 2n, right? Okay. I'm going to rewrite our mean approximate over here to make some space, just so we can compare later. 265 over 32. All right. Now, I'm going to distribute the 3 over 4n into each one of these. So I get limit as n goes to infinity of 33 over 4, right? And then that's going to give me 45 over 8n and 9 over 8n squared. But the limit is on this whole thing, right? The limit as n goes to infinity of the number is just going to be the number. But the limit as n goes to infinity of both of these guys that have n in the denominator, that's going to go to 0. So what I'm left with is 33 over 4. Okay? 33 over 4 is 8 1/4. So 8.25 is the actual area underneath that parabola between the x values of 1 and 4. Our mean approximate area, 265 over 32, I think was 8.28. Yeah, 8.28125. Okay? So the left and right hand sums were kind of close, but with a parabola it's difficult to tell if you have enough rectangles or not. But when you average them together, you can usually get pretty close with an approximate area there. And we have better methods of approximation, of course. There's other methods called like Simpson's rule and midpoint rule and trapezoid rule and stuff like that. But what you need to know for this is how to set up a left-hand sum, a right-hand sum, and then I usually just turn the right-hand sum into an area calculation with the limits by setting up your x counter and then taking the limit as n goes to infinity. Okay, so this is the actual area here. Where we're at right now is sort of, well, not sort of, it's a lot like, it's very synonymous with where we were when we first defined derivatives. You remember we would do the long version of the derivative and get the slope of the tangent line using the limits and the difference quotient, things like that. That's where we are right now, okay? Our area calculations, our summations, are not going to always be like this. And notice, all it was an x squared, right? We want to be able to do this for any shape. And even with an x squared, there's a lot of steps in there. Well, of course, I'm not skipping any so I can explain them all, but there is a shorter way. So don't lose hope when you see a calculation like this, is my point. You do need to understand how this sets up. You do need to understand why it works. You do need to be able to get through a basic one like this. But then after this, from here on out, we'll show you another way that I can get to this same answer with a couple of steps. Okay, obviously. I hope this section has shown you some new math with the sigma notation and with how to simplify it, and also a different way of looking at how we try to approximate areas. Stay tuned for more calculus that's actually linking this to antiderivatives.